Hello, ladies and gentlemen. We're going to do 3.5 today. We're going to be talking about limits at infinity. So our objectives are that we're going to determine our limits at infinity. That's unique. Alrighty. So what I want to talk about is I want us to remember end behavior. So the graph that I chose for us to go back and look at would be the logistic function. So if you'll remember, it's a cool function. It has two horizontal asymptotes, and it does something that looks like that. So this would be our logistic function. So if I wanted to talk about the end behavior, so maybe as x approaches positive infinity, and I'm going to say that this is y is equal to a, and I'm going to say this is y is equal to b, just so I have something to talk about. So as x approaches positive infinity, we would say that the function f is going to approach a, and as x approaches negative infinity, we would say that our function is going to approach b. So it's going to approach our horizontal asymptotes. Alrighty, so that leads us into going back and reviewing the rules for horizontal asymptotes. Okay. So for our horizontal asymptotes, remember that they can often determine the behavior of a function. And we're particularly interested in what happens at the extreme end. So maybe as x approaches our plus or minus infinity. So there are a couple of rules. So let's go back through those. The first one would be if I have a rational function, and so let's say I have a function divided by another function, and I know that the degree of g is bigger than the degree of f, then I know that I'm going to have a horizontal asymptote at y is equal to 0. That's actually a really handy rule to remember. On the other hand, if I have a rational function and I have the degree of f of x is equal to the degree of g of x, then my horizontal asymptote is going to be the quotient of the leading coefficients. And this one we see quite a lot. It's kind of handy. And then the last one of the three is if f of x and g of x, we still have rational functions, and I'm looking at the degree of f of x is greater than the degree of g of x, then I have no horizontal asymptotes, but I do have a slant asymptote, okay? And if you remember, that is a line or a curve that's going to push our graph, okay? And I can find it a couple of different ways, but sometimes we find it by long division, okay? So there are other ways to find a slant asymptote, but one of the ways that we can do it is by long division. Alrighty, so let's get a calculus definition of a horizontal asymptote. And it basically says that the line y is equal to L, so I have a horizontal line, is a horizontal asymptote of the graph of f if and only if the limit of the function as x approaches plus or minus infinity is equal to the horizontal line. So that would be our calculus definition of a horizontal asymptote. Alrighty. There is a limit rule that we need to go back and revisit. And basically, we're going to talk about it in terms of a horizontal asymptote. So if I have the limit as x approaches plus or minus infinity of a constant divided by x raised to some power. Well, if you'll notice, the degree in the bottom is higher than the degree in the top, because in the top it would be x to the 0. then because the degree in the bottom is higher, I have a horizontal asymptote at y is equal to 0. So remember, I would have a horizontal asymptote at y is 0. Therefore, the limit is also 0. And we use this particular rule to help us when we have to find the limit mathematically. All right, so let's do some examples. This one says find the limit. And we're going to be given the limit as x approaches infinity of 2x minus 1 over x plus 1. And I'm going to do it a couple of different ways. The first way is I'm just going to talk about the horizontal asymptote, and then I'm going to confirm it mathematically. Well, if you'll notice, the degree in the denominator is 1. The degree in the numerator is 1. The degree is the same. Therefore, the horizontal asymptote is just the leading coefficients. Well, 2 divided by 1 is 2, so the limit is 2. That didn't take very long. But let's say I wanted to do it mathematically, and you do have to be able to do it both ways. But sometimes when we're lucky, we get a shortcut. So I'm going to do the limit as x approaches infinity of 2x minus 1 over x plus 1. And what I'm going to do is I'm going to use this rule to talk about, so I'm going to divide every term by x, okay? So this is going to be the limit as x approaches infinity of 2x minus 1 over x, and then x plus 1 over x. The net effect of x and x is 1, so I haven't changed the value of the equation. I'm just going to make it look different. And then I'm going to rewrite it. So this is the limit as x approaches infinity of 2x over x minus 1 over x over x plus 1 over x. And if you'll notice, all I did is split up the individual expressions. Well, because the degree in the denominator is higher, this goes to 0, this goes to 0, this goes to 1, and this is going to go to 2. So the limit is 2 divided by 1, which is 2. All right, so let's just do a couple more examples, and again, I'm going to work on them both ways. So the next example, I want to do the limit as x approaches positive infinity of 2x plus 5 over 3x squared plus 1. And again, I'm going to do it from the horizontal standpoint, the horizontal asymptote, and then I'm going to do it mathematically. Okay? Alrighty. So if I look at this, I notice that the degree in the denominator is higher than the degree in the numerator. So the horizontal asymptote is 0. Therefore, the limit as x approaches positive infinity is 0. Ooh, that's easy. So now let's do it mathematically. And again, I'm going to try to use the same process. So I'm going to divide everything by the highest degreed term. Okay. So I'm going to do 2x, and I'm going to divide it by x squared, and I'm going to do 5 and divide it by x squared, and I just committed a terrible sin by not writing my limit stuff down, so I'll get there in just a sec. I'll squeeze it in, limit as x goes to infinity. Shame on me. Well, the degree in the denominator is higher. He goes to 0, he goes to 0, he goes to 0, and he goes to 3. But 0 divided by 3 is just 0. And I didn't get the indeterminate form, so I'm good to go. Alrighty. Let's do another example, same kind of process. Okay. So I'm going to do the limit as x approaches infinity. This is my example. Sorry, try to be consistent. Of 2x cubed plus 5 over 3x squared plus 1. So if we look at this one, we notice that the degree in the numerator is higher than the degree in the denominator, so I know that I'm going to have a slant asymptote. So I'm going to approach this problem by dividing by the degree in the denominator. So I'm going to do, this is the limit, and I'm not going to do the long division. I'll show you why. Of 2x cubed over x squared plus 5 over x squared over 3x squared over x squared and 1 over x squared. Well, because the degree in the denominator is higher, this is 0, this is 0, this is 3, and this is 2x. So if I simplify that, I have 2x in the numerator and I have a 3 in the denominator, so this is 2/3 x. And so I still want to think about the limit as x approaches infinity of 2x over 3. If I graph that line and think about it, okay, so I didn't graph the slant asymptote, but I'm graphing what's left over. This is a line that goes through the origin, right? Okay. And as x approaches positive infinity, the y value is approaching positive infinity, but because there's no limit to the growth of the function, because the function is going to increase without bound, then the limit, I'll write it over here, the limit of f as x approaches infinity does not exist because there is no boundary on the end behavior of the graph. Alrighty, couple of thoughts, things that we need to remember. So for our couple of thoughts, we want to look at the highest power in the rational function because that's going to drive the influence, or sorry, it has the most influence when determining the limit. So it has the highest power in the rational function, has the greatest influence. In our limit, and we're going to do the limit specifically as x approaches infinity, okay, and we could do plus or minus infinity, alrighty. The thing that's also nice to remember, and I'll move my paper up in just a sec, rational functions are going to approach the same horizontal asymptote as x approaches both positive and negative infinity. So just like on our example with the logistic function, sorry, that's a regular function, in a rational function, I might have a horizontal asymptote, and regardless of the direction, I'm going to approach the same asymptote. So then the next thing would be, like in the logistic function, regular functions or non-rational functions can approach different horizontal asymptotes as x approaches both positive and negative infinity. And again, the classic example of that is the logistic function, because as I approach, let me scoop my paper up, sorry, as I approach positive infinity, my function is approaching this asymptote, and as I approach negative infinity, it's approaching the lower asymptote. So rational functions and non-rational functions can have different limits as x approaches infinity. All right, so I do want to do another example mathematically just because it's a little bit tricky. So we're going to call this our tricky example. And just because the algebra is a little bit unique. So I want to do the limit as x approaches plus or minus infinity of 3x minus 2 over 2x squared plus 1. So again, the highest degree, if you think about it, if I'm taking the square root of x squared, the highest degree is actually x. So I'm going to divide every term, top and bottom, by x. So I'm going to do the limit as x approaches plus or minus infinity. And I'm going to do 3x minus 2 over x. And then I'm going to do, here's my radical, 2x squared plus 1. And I'm going to divide it by x. But if you remember from Algebra 1 and Algebra 2, and sometimes in pre-calc, I can't do this math because he's not in a radical. So I'm going to fix him and make him be a radical, and now I can put the two together. Alrighty? So I haven't changed anything because the square root of x squared is x, which is this x, so the net effect is 0, or sorry, the net effect is 1. But now because this is in a radical, I can bring it up into here. So now I have the limit as x approaches plus or minus infinity of 3x over x minus 2 over x over, and then I'm going to have the square root of 2x squared over x squared plus 1 over x squared, because now legally I can bring it under the radical. Well, the limit of this guy is 0. The limit of this guy is 0. The limit of this guy is radical 2. And the limit of that guy is 3. So the limit is 3 over radical 2. Alrighty? So if you'll notice, this is where it gets kind of entertaining. So that's the tricky algebra, and it was this little step right here. I have a 3x on the top, and I have a radical 2x squared, which is a radical 2x. So the degrees are technically the same, top and bottom. So then the horizontal asymptote is just the quotient of the leading terms. Well, my leading terms are 3 and radical 2. But that one is a little bit less weird to look at and recognize, but it is kind of cool because that's actually just our horizontal asymptote. All right, for the next example, we'll do a trig one, introduce a concept that we talked about in pre-calc. So this is the sine of x over x. I'm going to split this little guy up, and I'm going to rewrite him as the limit as x approaches infinity of 1 over x times the sine of x. Well, as x approaches positive infinity, that guy goes to 0. Well, if that guy goes to 0, then that guy goes to 0, so the limit is just 0. Alrighty, so here's what I wanted to bring back from pre-calc, because it actually looks really cool. This 1 over x is actually a damping factor to this, and what it does is the graph actually doesn't look like this, but it takes my sine function and it squishes it, and it damps it. That's a hard word to say. It damps it and pushes it closer to 0. So that's just something to remember from pre-calc, and we talked about the damping factor. Alrighty, I have one more example for us, and then one last thought, and then we're done. The next example, find the limit. So we're going to do the limit as x approaches plus or minus infinity of 2x squared minus 4x over x plus 1. So on this one, instead of dividing by x squared, I'm going to divide by x, just because I can, and I'm going to show you what happens. If you'll notice, the degree in the numerator is higher, so that means that I have a slant asymptote. So what I'm going to do is I'm going to divide everything by x. So I'm going to have the limit as x approaches plus or minus infinity of 2x squared over x minus 4x over x over x plus 1 over x. Okay? If I do this guy, he goes to the negative 4. This guy goes to 0. This guy goes to 1. And this guy goes to 2x. Okay? So in the denominator, I have 1 plus 0. So this is the limit as x approaches plus or minus infinity of 2x minus 4. Except you can't see the 4. So now what I want to do is I want to talk about the graph. So this is what I'm now trying to take the limit of. Well, this is easy peasy to graph. So I have a y-intercept at a negative 4. My slope goes up, and so my graph does something like that. Well, what happens as x approaches positive infinity? So the limit as 2x minus 4 as x approaches positive infinity is going to be positive infinity. And the limit of 2x minus 4 as x approaches negative infinity is a negative infinity. Besides the fact that there's nothing to limit the behavior of the graph, they both approach different values. Therefore, the limit of f of x as x approaches infinity does not exist. Alrighty, so we're done with examples, but what I wanted to do is just kind of give you one last thought. So we have done a lot with graphs, and we've done a lot with determining information and characteristics about our graphs from our previous sections. We know how to find extrema, okay, and I can do that with my first derivative test, okay. We know how to find intercepts. Hopefully you've known how to do that for a really long time. We know how to find symmetry, okay, and if in case you forgot, We can determine whether I get the original function, which is the y-axis, or if all of the signs are the exact opposite, then it's about the origin. So I know what type, oops, I spelled it wrong, what type of symmetry my graph can have. I know how to determine my asymptotes. I hate that word. I can't ever say it right. And we can really come up with a very accurate graph using all of our information. And then if we talk about the limits as x approaches infinity of our graph, then we know what the end behavior is doing. So I can actually come up with a really accurate image of a graph by using all of these different tools. Alrighty. And I guess I should have not forgotten, we also can talk about concavity because of our second derivative test. Don't want to leave that guy hanging out there, okay? So there's lots and lots of things that I know about a graph without ever having to use a calculator. Alrighty, that's it for today. I will see you tomorrow.